the generated charge will be transferred, travel to the electrodes. How this one happens, we know this one. This one has low work function compared to this one. When the work function is low compared to this one, the electrons all the time tend to go from higher work function to less work function. So some of the electrons in this part will be fused towards here. So there will be electron accumulation to this part, and also this one, this will treat like a hole. So there is going to be an electrical field from that side to here, to that side. Due to this electrical field, the electrons and holes will be collected, and the holes will be collected by this side, and the electrons will be collected by the cathode side.
But you told us that electrons is on the other side, you know? Yes?
Yeah.
You say the opposite, you say now. The final sentence.
I mean, so when you bring the anode and cathode material together, some of the electrons which are in this part will diffuse to here. So this side will treat like accumulation of electrons. So and also this side will treat like positive side. Yeah, there will be electrical field from that side to that side. So when the exciton is created, these electrons will attract the generated holes towards that side, and this positive side will tend to attract the generated electrons towards that side.
Why?
That side.
Why? Why?
Because of the matching between the work functions actually. Because when you bring two metals that have different work function, the electrons tend to go from a higher work function to lower work function. So some of the electrons will diffuse towards the low work function electron side, and when the electrons are accumulated one side, the other side will treat like positive charge. This is called actually matching of, I think, thermal level will be created. There will be match between them. So due to this electrical field, the generated excitons by this solar energy will be attracted by these electrodes.
So let me explain. Let me explain what is the anode electrode and what is electrode. Why do you call this one and what happens here?
Okay.
Basically, so simple. This high school definition. What happens in anode?
So the anode means it collects the positive charge normally.
But what I know, you know, actually, what does it mean? You know, anyway, so what happens? Oxidation or reduction?
I see.
This is the, so is there any relation in this oxidation reduction? So originally this comes from this definition.
Of course, if it's
what is the oxidation? What is the anode electrode?
I think the oxidation. So
yes, right. Oxidation is what happens.
Yeah, this is oxidation process, and the other one is reduction.
Means that oxidation. What does it mean? Oxidation. One electrode, so what happens?
If it accepts the electrons?
No, it leaves, it loses electron. This, okay, loss of electron is oxidation. This is a process.
Okay. Sorry, yeah. Okay, gaining electron means reduction.
Reduction.
Okay, you are right.
This is a process, you know.
Yeah, you are right. Yeah.
Oxidizing agent and reducing agent is different thing.
Yeah,
it's a process, okay. It means that in anode, there is an oxidation. Yeah. Electron losing, as we know. We know. And the cathode electrode is reduction taking electrons. This is the simple but very important thing.
Yeah, you are
then
right.
Explain everything accordingly. And then match what is I don't know if this is the case.
Okay, that is the basic working principle. So I just want to emphasize one more important thing here. I have already talked about the basic working principle of a solar cell. If you look at this one, there will be generated electrons and holes during absorption of photon. So when the exton is formed, it doesn't matter if it can be either electrons or holes. It is important that the electrons, for example, should be collected towards the aluminum electrode. Yeah. So to be able to do this, there should be a pathway, which is which is called as calculated pathway. Otherwise, the electrons will be trapped. So I mean, if you look at this one, the line represents the donor material, while the brown circle represents the acceptor material. When the photon is absorbed, there will be exciton, and so the electron will be transferred to the LUMO of the acceptor material. If you look at this one, there is a way for electron to be collected by the aluminum electrode. If there is no way, then the electron will not be able to travel to that side. Similarly, the prepared host should have a way to travel to the anode electrode, so this is quite important as well.
So what happened to the exciton in this case? Suppose the light comes and then you create exciton. So electron goes to another electrode, holes goes to another one. So what happened to the exciton?
So the exton then, in that case, the binding energy will be overcome when this process happens. So you will have, you will collect the charge, then you will have electricity. Normally, if this process does not take place, then they will recombine. Then the photons will be emitted. If they are collected by the electrons, then you will have electricity.
So what happened to the exciton?
So
Do you understand
what happened?
So what's the lifetime of exciton in this process?
Oh, I see. I think it is around 30 seconds, but I'm not sure about it exactly. This process happens in a very short time. It may be around 30 seconds, but I'm still not sure about it.
So this means exciton somehow dissociates to electrons and holes, right?
Yeah, of course. I
So
was telling this one.
Okay, would you define what is exciton and what is the difference between exciton and electron?
Exciton is the pair of electron and holes. So there is a Coulombic interaction between electron and holes.
Let's go back to the previous slides.
So this is exciton.
So it means that the holes and the electrons.
Yeah, of course, this is pair of holes and electrons.
Okay, in spatial position.
Yeah.
So it means it has the holes positive and the electrons negative.
Yeah.
So, but how do we sign them? How do we show them, label them? As A minus, I have seen this is electrons. Is A minus?
No, the whole system is called as exciton. So this is hole and this is electron. This group is called as exciton.
Okay.
What's the exciton energy?
It is thought that it is between 3.3 eV and to 3.5 eV normally.
For what? Which material?
Which
Is it constant or what?
as far as I know, it's I think for P3HT, poly-3HT hexylthiophene, but I don't know any other materials. I said there is different range, so we cannot tell this one the binding energy is exactly that value, but the one that I have read so far is 0.3 to 0.5 EV.
And this is A minus is electron, I think. Is that right?
Yeah, of course, yeah, you're right.
Okay, what is the exciton energy? So this is the energy to break down this to
So I was trying to tell you about this one.
Yes.
If you look at this one, there is still interaction between this electron and holes. Yeah?
This is it's an attraction.
Yeah, attraction, of course, Coulombic interaction.
Yeah.
So, because this is positive, this is negative.
So
But the break, to be able to break this bind, you have to, there should be at least, I think, 0.7 EV
yeah, to bring
between
it up.
lumo level of the donor and acceptor material. Okay, so there are lots of parameters to optimize a solar cell. So I will simply classify them into two groups. So the first one, the properties of the material, and the other one is the microscopic structure of the bulk heterojunction. So in the first part, this is related to band energy levels of the materials. This is related to morphology of the material. So there should be homogeneous structure, otherwise the power conversion efficiency could be less than you desire. So the efficiency is defined as the maximum power generated by the solar cell to incident the input power actually, which is coming from the solar cell. So we have this formula. So this is short circuit current density. So you can change this one by simply tuning the transfer properties of the materials. So this is related to mobility, and VOC is the actually maximum voltage that can be obtained by the solar cell. This is related to the difference between the LUMO of the acceptor material and HOMO of the donor material. So you can change this one by simply tuning the electronic levels of the donor acceptor systems. The fill factor is another important factor. So this is defined as the squareness of the IV curves of the solar cell. I mean the ratio of this area, so which is the maximum power generated by solar cell, to product of the short circuit current and the open circuit voltage. You can change this one as well by simply tuning the contacts and morphology of the solar cell. And the power input can be changed by spectral absorbance and absorbing more light.
What's VOC? What does it mean, VOC?
This is open circuit voltage. I mean, when you connect this one to a load or to a capacitor, when you shine a solar cell, there will be current generated by the solar cell, but at some point the current will be zero at some potential. So this is called maximum potential, and this is called open circuit voltage.
What does it mean? Why potential current goes to zero? I couldn't understand.
Because as I told you, when you connect this one to a capacitor, the solar cell, if you think this one, so you can think this one as open circuit. So this, at first step, when the capacitor is fully discharged, the generated current will be collected by the capacitor. But at some point, there will be potential difference between the capacitor. So at that point,
why do you need a capacitor to?
I just want to simplify it. I just want to give you.
We are getting more complicated.
Just give like a simple example, like a resistor, just a load.
Yeah, you can think this one.
Yeah.
As well.
The capacitor is a little bit more complex. I mean, just forget about that.
Okay.
What is open circuit? I wanna know this. What's open circuit?
You know this one, a solar cell or a device that has two electrodes. One of them is positive and the other. If you don't connect them, this is open circuit. When you connect this one, this will be short circuit.
This is it?
Yeah.
This is what you have to say that. Why do you need capacitor? Okay, wow.
Just the difference between the potential, that's all.
Yeah,
This is no current passing through it.
yeah, of course. Yeah.
So this in electrochemistry is also possible to see that because there is no current growing or something. Okay.
So in order to enhance the device efficiency, you can optimize the properties of the materials. So the first step is the matching solar spectrum. So you know this one, in solar spectrum there are wide range of the photons having different wavelength. So when you decrease the energy band gap between the HOMO and LUMO level of the donor material, you will have more generated excitons because the band gap will decrease and low energetic photons, which are going to be the near infrared photons, will be able to excite the electrons from HOMO to LUMO level of the donor material. And also the relative position of the energy levels of the donor and acceptor can be changed to enhance the power conversion efficiency of a solar cell. And optimal offset that we were talking about this one, so this should be at least 0.5 or more than 0.5 EV. Normally the general used materials, which are P2HT and PCBM, the difference between LUMO of these molecules are 1.1 EV. So this is called as offset band gap. This is quite important. So another factor that affects the power conversion efficiency of a solar cell is, of course, the morphology of it. You have to decrease the diffusion length when you create your active area. Otherwise, normally the diffusion length of an exciton is around 5 to 7 nanometers. If the distance between if you look at this one, if this distance is more than, let's say, 10 nanometers, then the excitons will not be broken, so you will not be able to collect the generated charge. So this is quite important. You have to decrease the diffusion length. So
okay, now another point. What is diffusion?
Diffusion.
So what's happened? Diffusion. So you should explain what is diffusion here. In that case, the diffusion length, then we can understand better. What is the diffusion length? I mean, the diffusion from which place to another place, you know.
For example, for that device, the diffusion is called as the traveling of electrons from high lower work function to low work function. We can take this process as diffusion process. The electrons will be diffused towards the interface.
Through the material, you know.
Yeah, of course.
And this material, depending on the material also,
yeah.
What kind of material, and also the liking, of course.
Yeah.
There is diffusion liking, you know.
Yeah.
The minimum that has to be there. After that one, diffusion, there is no more diffusion, you know.
Yeah, you are right.
Okay, that one, this minimum, this maybe that's the reason, you know.
Okay.
Because after that diffusion length, electron on the whole, either one of them or two of them, it doesn't matter, and it goes down, and it's going down.
Yeah.
So it's kind of this is the and if you just divide it by this length by the speed of light, and it means it gives the lifetime.
Yeah, lifetime. So the other factor is, of course, the presence of percolation pathway. So as I already told. So what is it? This is the problem statement part. You know this one, normally the silicon-based, which are the inorganic materials, solar cell, are highly used right now, but it doesn't fulfill, and it is quite costly because it requires vacuum environment. Therefore, organic materials, which are non-toxic and flexible and abundant, and because they are low cost compared to the silicon-based solar cell, it is better to use the organic materials instead of inorganic materials. So the efficiency of solar cell, organic solar cell, has been increasing within the last years. So therefore, it attracts the attention. So in order to prepare organic solar cell,
where is the literature here? You should have shown the efficiency increases. So how? Where is the literature here?
Normally it's here. So I should put this one in a previous slide, I think.
Every slide, every sentence that you got from somewhere else, you should refer it, you know.
Yeah, you're right.
This is it. So it means that
Before you come to the problem statement, you have to show literature and come up to the problem, okay?
The general technique which is used to prepare the organic solar cell is the spin coating technique. It's quite cheap and it serves highly efficient organic solar cells. But the problem is that you cannot transfer this technique to industrial, mass production. So therefore, I thought we should use the roll-to-roll processes, which is cheap and ease of fabrication, is to be developed. And
let's come to literature first. Please explain this one, and then come up here.
here. So these are the. I think if we come here, then this is completely related to roll-to-roll processes, not the traditional methods. Therefore, we may confuse if we start from here. These are the power conversion efficiency of the solar cell, which is fabricated by using inkjet printing technique. So there are different parameters that researchers try to understand. If you would like, we can. I'll try to
explain it everything. So this is the basement of your thesis, right?
Okay. So there are different materials which is used to prepare the organic solar cell. So inkjet printing technique is normally used to prepare homogeneous active layer, but the advantage of this one compared to spin coating technique, this is faster and this is cheap as well. You can transfer the results to the mass production by using this technique. The most efficient solar cell that has been obtained by using inkjet printing technique is 3.7. So in the first study, they have prepared a solar cell by using this material. They have compared the efficiency of them, efficiency of the solar cell which is prepared by inkjet printing technique and spin coating technique. And they have also worked on different parameters as well. The inkjet printing is used to prepare more homogeneous structure, and also it is used to prepare grid-like structure. I mean, you know this one, the research is trying to replace the indium tin oxide, and in order to do it, they are trying to create grid-like structures. So this technique is used to create grid-like charge collecting electrodes. So,
what are the problems that you would like to solve in the inkjet technique? So I explained them with the references.
The first aim of my study is to enhance the already prepared solar cell. I mean, I will use different materials, but also I'm going to decrease the width of the solar cell. I just want to insist on this one. when you decrease the width of the solar cell, the series resistance will decrease as well. So my purpose is to decrease the series resistance and increase the power conversion efficiency. So I think I should start from the other slides. Otherwise, there will be no connection between.
So why did you put this? First of all, you have to come up with a problem from the literature to be able to solve it. You understand what I'm saying? And then you can define your problem statement. Okay, go ahead.
So I just try to emphasize why we should use the roll-to-roll process instead of spin coating technique. Because if you cannot transfer the results to the mass production, so it will not have, it's going to be meaningless because it doesn't matter, it is quite efficient. So you have to transfer the large-scale solar cells to mass production. So in this study, I'm going to use two different methods to prepare solar cells. So one of them is the inkjet printing technique, and the other one is the slow tie coating technique. So this is why I plan to use inkjet printing techniques, because it is already established technology, and you don't have to create a vacuum ambience because it doesn't require any vacuum ambience, and it is quite cheap. And one of the most advantageous part of this technique is that it serves you, it enables you to create any structure. So you can create grid-like structures by using this one without sacrificing the power conversion efficiency of a solar cell. So digital patterning feature is quite important for inkjet printing technique. So the other one is the slow tie coating technique. They have the similar advantage, but you can use this technique. This is quite faster compared to the other technique, and also you can create one-dimensional structure. So this is very useful to prepare solar modules which are serially connected. So therefore, I'm going to use the slot tie coating technique to prepare my organic solar striped cells. So my aim, the purpose of my research is to design and develop highly efficient, ultra-thin and narrow organic solar striped cells by using slot tie coating and inkjet printing technique. And in order to fabricate the solar cell, I'm going to also develop the related layering methods for fabrication and characterization of the solar cell. The most important thing here is that the size of the solar cell that I will try to fabricate is going to be around 100 micrometer. So to reduce the size of a solar cell, to reduce the serial resistance, so I will try to develop a scheme which is given in the upcoming slides. So these are the literature, these are the studies that has been done by using inkjet printing techniques. As I told you before, this technique has been used for different purposes, especially to prepare homogeneous thin films. This technique is used to prepare both the electrodes and active layers. So the researchers used this technique to prepare homogeneous active layer, and also they tried to create grid-like structure in order to replace the indium tin oxide. Because in order to prepare indium tin oxide, you have to use vacuum environment, so this is also difficult to transfer to the mass production. So one of the highest efficient solar cell that has been done, obtained by using jet printing technique is 3.7%. So these are the list of the studies that are about the organic solar cells based on the slot die coating techniques. In this technique also the same parameters has been studied. And firstly, if you look at this one, the highest efficient solar cell is around, I think, 3.2%. So generally zinc oxide material has been used, has been studied by using slot die coating technique. So this is the methods and procedure slide. This is about it. If you look at this one, I'm going to try to prepare that kind of structure. So normally in the literature, the size of these solar stripes, this is called solar stripe, is around 1 millimeter by slot die coating and 200 micrometer by inkjet printing technique. So if you look at this one, this is polyethylene terephthalate, and this is indium tin oxide and PWSS, and also P2H, the PCB active layer, and this is the aluminium. So my purpose is to decrease this width. So because the length of this stripe is not important. What is important here is that the charges are collected towards this side. So if you decrease this one, the series resistance will decrease, and then the power conversion efficiency will increase. So as I told you before, I think the thinnest structure obtained so far is around 1 millimeter wide. I will try to decrease this side to 100 micrometer. In order to do this one, I will sorry. In order to prepare that kind of stripes, I'm going to use these hats. This is called as slot die coating hats. So this one includes a mask. So I'm going to decrease the width of this mask to the 100 micrometer to prepare that kind of structure. I'm sorry about this one. I should have put this one to the previous slides. So for the first step, I'm going to fabricate a solar cell by using spin coating technique. So I will use this one as reference solar cell, and then I'm going to try to fabricate that kind of solar cell, and I'm going to characterize them, and I will find the power conversion efficiency of this one, and then I will compare this result with the one that has been prepared by using spin coat technique. And then I'm going to decrease the width of this one by developing the mask which is used in slot die technique, and then I am going to prepare the solar modules, which is the serially connected solar stripe cells. So this is basic principle of inkjet printing and slot die coating technique. If you look at this one, there is a piezoelectric nozzle here. So you can create any structures by using inkjet printing technique. So you simply apply a voltage to here. When you apply voltage, this will be bent, and then the drop of the ink will go towards the substrate. And also, if you look at this slot die coating technique, you are going to inject the ink here, towards here, and also it is going to transfer towards the this offset web. So the thickness of this one is defined as the dry thickness of this one is defined as here. This is the flow rate of the flow rate of the substrate. Actually, this is flow rate of the ink, and